Assalamu alaikum and hello. This video is for Database Systems course, subtopic Database Recovery and Backup Strategies. We will explain how databases recover from failures. We will look at the role of the recovery manager, undo versus redo operations, backup types, failure types, and how DBMS ensures durability even after a crash. Databases must remain consistent, available, and durable. The recovery manager's goal is to ensure that committed transactions are never lost and incomplete transactions do not affect the database. Recovery mechanisms allow the DBMS to restore the database to a correct state. Core responsibility restores the database to the most recent consistent state after a failure. ACID enforcement specifically handles atomicity, all or nothing, and durability, persistence. Key operations: logging all actions, write-ahead log. Restoring the database after crashes. Undoing incomplete transactions. Redoing committed transactions. Managing checkpoints. The recovery manager works closely with the transaction manager to track transaction status and ensure ACID properties, especially atomicity and durability. Types of failures. 1. Transaction failure, caused by logical errors, invalid inputs, and deadlock detection. Only the affected transaction needs undo. 2. System or software failure. Operating system crash, DBMS bug, memory error. Active transactions lost from memory. Recovery uses global undo and redo. 3. Hardware failure, disk crash, CPU failure, memory corruption. Requires restoring from backups, logs might be lost. 4. Programming exemption, application software errors. 5. External failure, natural disasters, fire, power outage. Requires strong disaster recovery plan and off-site backups. Each failure type triggers different recovery strategies, from simple rollback to full database restoration. Write-ahead logging is a fundamental mechanism used by DBMS to ensure atomicity and durability in transactions, especially when the system crashes. The golden rule of recovery: no modification goes to the database disk until it has been written to the log file. This ensures the DBMS always has a reliable record of what was supposed to happen. Force log at commit. Transaction is only considered committed when its log record hits stable storage. Checkpoints. Periodically flushing dirty pages to disk to reduce recovery time. Log sequence numbers, LSN, ensures logs are applied in the exact order of operations. WAL allows DBMS to 1. Recover committed transactions, redo. If a committed change was not written to disk before a crash, the DBMS reads the log and reapplies the update. 2. Undo incomplete transactions, undo. If a transaction was not committed yet, the DBMS reads log entries and reverses any partial changes. With WAL, the log becomes the source of truth for recovery. Undo versus redo operations. Undo, reverse uncommitted changes, used when a transaction fails or system crashes before commit. Redo, reapply committed changes, used when a transaction committed but its changes were still in the buffer, volatile memory, and not yet flushed to the disk. The system reapplies these from the log. Undo protects atomicity. Redo protects durability. This table summarizes how a database recovery system handles different transactions after a crash, based on whether they were committed and whether their updates were written to disk. T1 committed, and its changes were already flushed to disk, so no recovery action is needed. T2 committed, but its updates were still in the buffer, not yet written to disk. So the system performs a redo to reapply the committed changes from the log. T3 was active and uncommitted, with some partial updates written to disk. So the system performs an undo to roll back those incomplete changes and restore the original value. T4 was also active and uncommitted, but none of its changes reached disk, so the system simply ignores it because everything was still in volatile memory and will be lost naturally after the crash. Partial undo refers to reversing the effects of a single active transaction during normal database operations. It is typically triggered when a user issues a rollback, an application encounters an error, or the system needs to revert back to a defined save point. The goal of partial undo is to cancel only the specific work of that one transaction without disturbing other transactions in the system, allowing the database to maintain consistency while still continuing normal processing. Global undo occurs during system recovery after a crash. When the database restarts, it identifies all transactions that were active, uncommitted, at the moment of failure. Since these transactions did not complete successfully, the system must reverse all their effects to restore a consistent state. This process is called global undo because it applies to all incomplete transactions, often called losers, ensuring that only the effects of fully committed transactions remain in the database after recovery. A full backup, level 0, is a complete copy of the entire database at a specific point in time. Since it includes everything, it takes the longest time to create and requires the most storage space. However, restoring from a full backup is the simplest because the system only needs this single backup file to return the database to its saved state. This type of backup forms the foundation for all other backup strategies. A differential backup, level 1, and log backup build on top of the full backup to offer faster, smaller, and more flexible recovery options. A differential backup stores only the data that has changed since the last full backup, making it quicker than a full backup and needing less space. To restore, you need the full backup plus the latest differential. Meanwhile, log backups continuously record all changes in the transaction log, enabling point-in-time recovery, PITR. They are the smallest and fastest backups to create, and during a restore, they allow you to recover the database to any exact moment before a failure by replaying these logs. Most enterprise systems combine full plus differential plus log backups to balance speed, storage, and recovery time.
In conclusion, effective database recovery is essential for maintaining data integrity, ensuring system reliability, and guaranteeing that committed work is never lost, even in the face of failures. By combining structured backup strategies, robust logging through mechanisms like write-ahead logging, and well-defined recovery processes such as undo, redo, and checkpointing, modern DBMSs are able to quickly restore operations and protect against data corruption. Understanding these concepts not only strengthens system administration and troubleshooting skills, but also highlights the critical role recovery mechanisms play in supporting stable, dependable database environments. Thank you, and see you again.